Good day, my name is Irina Bobkova and I'm a senior researcher in Institute of Solid-State Physics and also an associate professor in Moscow Institute of Physics and Technology. Today I would like to tell you about our new work done in collaboration with Alexander Bobkov from Moscow Institute, from Institute of Solid-State Physics in Chernogolovka, and with Grigory Bobkov, who is now a student of Moscow Institute of Physics and Technology. The work predicts a fundamentally new type of long-range interaction between magnetic moments in a coupled system of superconductor paramagnet superconductor Josephson junctions. The outline on the talk is the following. At first, I'm going to give you a brief introduction devoted to known so far mechanisms of indirect interactions of magnetic moments via a superconductor. Then I'm going to tell about our work, and to begin with the description of the system under consideration and a qualitative physics of the effect. After that, I'm planning to discuss how the energy of different magnetic configurations depend on the superconducting phase. And then I will consider a dynamical problem of magnetization switching controllable by superconductivity. At the end of my talk, I am going to present my conclusions. Nowadays, hybrid structures consisting of superconducting and magnetic materials are being actively studied. The reason for this interest is the possibility to realize in such hybrids properties and effects which are not possible in individual materials. In particular, one of the actively developing directions is the search and study of physical principles that can provide an indirect long-range interaction of magnetic moments through a superconductor. The indirect exchange interaction of magnetic moments in a non-superconducting metal, the so-called RKKY interaction, is of course very well known. However, the stronger oscillation and decaying nature of this interaction at the atomic scale allows to achieve interaction between the magnetic moments at distances not exceeding a few nanometers in layered structures. Making use of superconductors can enlarge this scale. It was first pointed out by Dijen that if one changes the non-magnetic layer by a superconductor, the antiferromagnetic configuration should be more favorable. The reason for this is that with such a mutual orientation of magnets, superconductivity in the interlayer is less suppressed. The characteristics length scale of such interaction is the superconducting coherence length psi, which is of the order of tens to 100 nanometers depending on the particular superconductor. It has also been reported that for D-wave superconductors, cuprate superconductors, the effective coherence length of nodal bound states mediating the interaction can be strongly enhanced with respect to Xi. But the Xi by itself is very short in cuprate D-wave superconductors. Then it has been also proposed to use not the proximity, but the so-called electromagnetic proximity effect to establish a coupling between magnets. Its essence is the appearance of Meissner currents in a superconductor in response to the presence of an adjacent magnet. The characteristic scale of such an interaction is a magnetic coherence length lambda, which is also tends to 100 nanometers. The interaction between localized magnetic moments in a superconductor also has been studied, and it was shown that there is an additional to RKKY contribution decaying exponentially over the coherence length Xi and with a weaker power law suppression, which is due to the overlapping between U-Shiba-Rusinov bound states localized at different magnetic impurities. And this interaction also favors antiferromagnetic alignment. For all the discussed superconducting mechanisms, the interaction scale is restricted by the fundamental superconducting scales, the coherence length Xi or the magnetic penetration depth lambda. Now we propose another fundamentally different mechanism. It can be realized in a system of two coupled Josephson junctions via ferromagnetic interlayer, the first one and the second one. Each of the interlayers is described by its uniform magnetic moment, M1 and M2. The phase difference between the superconducting leads is chi, and the phase of the middle superconductor is psi. Our main result can be formulated as follows. In such a system, a long-range indirect interaction occurs between magnetic moments M1 and M2. Both ferromagnetic and antiferromagnetic configurations can be energetically favorable. The sign of the interaction is controlled by the phase chi. The special scale of the interaction is not restricted by the coherence length or the magnetic field penetration depth. The mechanism of the interaction contains two key ingredients. The first is that they need a coupling between the magnetic moment and the superconducting phase in each of the SFS junctions. In order to get it, the current phase relation should have an anomalous ground state phase shift, chi naught, which depends on the magnetization direction. Josephson junctions with anomalous ground state phase shift are well-established subject and can be realized in Josephson junctions via ferromagnets with spin-orbit coupling of any physical origin. For topological insulator-based Josephson junctions or Josephson junctions with Rashba type spin-orbit coupling, chi naught is proportional to the in-plane magnetization component perpendicular to the current direction. If we inspect the Josephson energy of such a junction, we see that at a given phase difference, it depends on the magnetization direction. The degeneracy between My and minus My is removed. The second ingredient is the middle superconductor coupling two Josephson junctions. It has a single microscopic quantum phase which interacts with the both magnets, thus mediating interaction between them. Even if the superconductor is quite long and we have to take into account the phase gradient due to the supercurrent flowing via the system, it does not influence the results qualitatively. Now, let us consider how the energy of the ground state of the system depends on the superconducting phase chi. The basic equations are very simple. The energy of the system consists of the Josephson energy contribution of the both junctions and the magnetic anisotropy energy. We assume an easy axis type anisotropy with the easy axis aligned with the y-axis. The second equation is just the current conservation across the whole system. It determines the phase psi of the middle superconductor. So from the system, we obtain the following typical dependence of the system energy on the superconducting phase chi. We see that due to the Josephson energy contribution, the degeneracy between the state with opposite My is removed. The definition here means My plus 1, plus 1, plus 1, minus 1, anti-parallel configuration, and this green is minus 1, minus 1. For each of the branches, solid parts of the curves correspond to stable solutions representing local minima of the energy with respect to M1 and M2. And dash parts correspond to the absolutely unstable states, local maxima. It is seen that the mutual orientation of the magnetization in the lowest ground state of the system depends on chi. It is minus 1, minus 1, then it is anti-parallel, and then it is plus 1, plus 1. That means a phase-dependent magnetic interaction between the magnets. That was an equilibrium consideration. Now let us consider some dynamical problems. We will focus on two situations. The first one is when the phase chi is changed adiabatically, and we investigate the induced magnetization dynamics. The second situation is when we fix the phase and reverse one of the magnetization and study the dynamics of the other one. For solving the dynamical problems, we need the following equations. The first one, is again the current conservation, which determines the dynamical phase psi of the middle superconductor. But now the current via each of the junctions consists of two contributions, the Josephson current and the normal current due to the voltage generated at the junctions by the time dependence of the phase. The second basic equation describing the dynamics of the magnetic moments is the Landau-Lifshitz-Gilbert equation. The effective field driving the dynamics contains the anisotropy field and also the spin-orbit torque contribution proportional to the electric current flowing through the junctions. Let us consider the adiabatic phase variations. Here we start from the anti-parallel ground state, change the phase chi slowly, and plot the evolution of the both magnetizations, and one in blue and in two in yellow. It is seen that the magnetic configuration can be switched by the phase variations. The part of the evolution enclosed into this dashed rectangle is put here on the equilibrium energy branches, and we observe that the switching can occur via two different mechanisms. The first one corresponds to these two transitions and is then the stable magnetic branch just becomes absolutely unstable. And the second mechanism corresponding to this transition is a bit more involved. It is realized via the abrupt change of the middle superconductor phase psi by pi and subsequent jump from the unstable to the stable branch. More details can be found in the preprint. Now, let us consider the situation when the phase is fixed. We start from the antiparallel state and at t equals 0, abruptly reverse one over magnets and fix it by external means, for example, by a magnetic field. This configuration is not stable at a given phase. Therefore, the second magnetization starts to evolve, and we end up with the final equilibrium antiparallel configuration with reverse magnetizations. The time evolution of the both magnetizations is shown here by the corresponding colors. It is seen that the time evolution of the second magnet, this blue curve, is not determined by the characteristic time of the magnetization dynamics, but in general is much slower. Now, we also start from the antiparallel configuration and reverse the red moment. But now it is not fixed and can evolve freely. In this situation, we can end up with two equiprobable final configurations. The corresponding time evolutions of magnetic moments are presented here. Okay, now I'm ready to formulate my conclusions. First, a mechanism of long-range magnetic interaction via the superconducting phase in coupled SFS Josephson junctions is proposed. The special scale of the interaction is not restricted by fundamental superconducting scales of coherence length and penetration depth. In fact, at the moment, we do not see a fundamental restriction of the scale. Second, the mechanism is based on the coupling between the condensate phase difference and the magnetization realized via the anomalous phase shift and the macroscopic character of the superconducting phase, which interacts with both magnets, thus mediating the interaction between them. And third, the mutual orientation of the ferromagnetic interlayers can be controlled and manipulated via the superconducting phase. And thank you for your attention. I will be glad to answer your questions.